So we're going to hear from Gautham Narayan, and obviously we're all very familiar with the idea of brokers. People have been talking about them for years, particularly in the context of the fire hose of information that will be coming from the telescope formerly known as LSST. And I think, Gautham, I'm right in saying that you're going to give us an idea of some of the cool things that you can do with brokers.
It's not actually so much about brokers, so much as getting beyond them and what they can't do right now.
Yeah, sorry, but what you can do when you have brokers.
Sure.
Okay, so take it away.
All right. So thank you all for having me today. This is not my first talk at SCiMMA, and this is not, like I said, principally broker-focused talk. So if you are interested in sort of a state of play for the broker ecosystem right now, there is a talk that I gave at the summer workshop in May of this year, again at SCiMMA, and there's, thankfully, since you folks record the videos, there's a YouTube link that sort of gives you a much more detailed summary of what brokers do, what their capabilities are, what the different brokers are that are out there, and so on and so forth. But this talk is really not so much about brokers so much as it is about what brokers can't do and what SCiMMA, I think, should think about building next as Hopscotch moves from beta to sort of a more mature product over the next couple of years. I do want to start with the brokers just to sort of to bring everybody up to speed and sort of put everybody on the same page as to what the issues with them are. So I'll focus on the broker that I'm a part of, the Antares broker. And this is a project that's been developed at NOAA Lab, formerly NOAO, in Tucson, together with the University of Arizona. When I moved from there to Space Telescope, sort of development moved along with me to Space Telescope and now to Illinois, where I've gotten my conspirators at NCSA to start working on this project as well. And soon we hope to be actually running a copy of Antares at NCSA. So Antares manages alert streams, and it is doing that right now with live alerts from the ZTF public survey. It adds contextual information from alerts, so I mean existing catalog matches, and it tries to characterize those alerts. There are, for example, Python packages that compute all sorts of features for individual light curves, things like period for variable stars, amplitude, kurtosis, all of that good stuff, but also things that actually try to sort of fit smooth splines to the light curves and look at the morphology of the shape of that light curve to see if it belongs to any particular classes. These filters can be simple things like just a few if statements to much more complex neural networks that have been containerized and uploaded into our Antares system. And Antares sort of will rank these things and then distribute alerts to anybody that wants to subscribe to it. Right now, that distribution is happening through Kafka, but this could easily be Hopscotch instead. There's no particular reason we're stuck with Kafka for this. And the key thing that Antares does differently from many of the other brokers is let you write your own filters. So you can write your little bit of Python code, upload it to our system. It runs as part of our pipeline on pretty much every alert that comes in from ZDF that passes minimum quality thresholds. And your code can decide what you want to do with that alert. You might decide this is an interesting object, let me trigger on it. Let me go get some follow-up spectroscopy, or you might say, well, send me a text message because this is the most important object this century, and I need to know whatever it is, whenever it is during the day, so if you found the galactic supernova or whatever. Or you might just say, well, send it into a stream, and I'll have a grad student look at it sometime during the day, and that's totally fine. The key is that it really enables you to do your science. So there's an element of offering public compute on a live alert stream. And of course, the reason this is all interesting for MMA is that we can take optical alerts from surveys like ZDF, but also other sources such as Assassin or other public surveys, and correlate them with, say, gravitational wave triggers from LIGO. So every time LIGO puts out a sky map, we get a notice, GCN notice, that lets us download that sky map. And we have code to automatically look in that SCiMMA, look at alerts within that region in either the 90% credible region or the 50% credible region for up to a week after the event. We can sort of only look at neutron star, or neutron star black hole events if those are of particular interest to find an optical counterpart. And we can look at any alerts that go off and actually again look at the morphology of the light curves and decide whether we want to trigger on them or not. If there's a similar high energy trigger from say something like IceCube around the same time, we can correlate that information as well. And so you can use the Antares system. It is formally still in beta, but this is very much beta as Google defines beta, where 1.0 people have been using it. You can go to the version of Antares that's on that URL, but I'm going to take you there in a second in any case. So I'm going to quickly switch to sharing from my browser to my browser rather than to a screen. So just to plug how this entire system works, I wanted to show you this object that hit the news essentially yesterday. And it's focusing on research done by a colleague of mine at Northwestern. So it's talking about a supermassive black hole that spaghettifies a doomed star in a tidal disruption. Great title, right? And looking at this thing, it identifies the object as 802019 QIZ. Now, for those of you who are not familiar with these postal codes for things like tidal disruption events, 80 says that that's a transient event. And if I go to the transient name server, which is the IAU blessed resource for identifying a transient name uniquely with an array and deck, I can get its coordinates. And so I'm just going to highlight those here. And take you to the Antares page, which has, all sorts of alerts that you have that are sort of live within ZTF. You can pick the ones that only have cross matches with a particular catalog, for example. You can search for a particular object ID. You can demand that alerts be within some particular time range. But here, all I'm going to do is actually just paste those coordinates in. So nothing fancy, not even going to change the default radius. It's going to do a clone search, and very quickly I get my results for this object. I pull up the particular page. I get links to external catalogs, a little array and deck map for all of the detections that ZTF has, a cute little Aladdin applet, and of course the light curve of the object from ZTF. And you can download all of this. You don't have to do this through a web interface at all. You can do this all through a Python API. And so within seconds, if you have an array and deck, you can get all of the photometry from ZTF and see the evolution of this event. The other thing that you should notice is this event has associated tags. So for example, we identified it automatically in Antares as a high amplitude transient candidate that was extragalactic. And so it has all of those particular tags associated with it. And if you wanted to, you could simply go look at all the tags we have and find other candidates that match the same exact criteria or match other criteria. So for example, if you cared about young, fast transients, you could simply pick those. But high amplitude transient candidates are interesting. And so let's click on ULOCA for them, and you'll automatically get a list for all of those sort of events. And so very quickly, you can write filters that not only find individual objects, they can find other objects in the data stream that look similar. And that's a powerful thing. Okay, so I'll stop there with the brokering for a second and go back to my slide presentations. So hopefully with all of this, I have been a good salesman and told you that brokers do all of this cool science and you definitely need them. But the problem that's been churning in my mind is that there are things that brokers don't do. And we need as a community, and I need as a scientist myself, so I want to build this stuff. And can multiple tags be applied to a given event or candidate? Asked Adam. Yes. Formally, I think there's some relatively huge limit for the number of tags because SQL has some limits on what you can store in the database, but it's unreasonably large, so you can effectively be free with tagging an event with anything you like. And tags can be declared in each filter. So each filter declares its own tags and says, I will be creating a stream that other people can access with this particular name. This lets us, for example, prevent filters from having the same name for a particular output stream. So if one person has a stream that is only for their group and is created by their own filter, no other filter will put objects into that stream. So the problem with all of this is, again, actually kind of visible from the diagram that I showed you for this broker ecosystem. And it's the cyber infrastructure that we have has already become fragmented with a whole bunch of standalone components that don't actually talk to each other really well. So there are 3 to 5 large broker teams, and I had a slide in my talk in May comparing and contrasting the features they have for each other. But there's a huge amount of redundancy because they're all doing more or less the same sort of thing. They're all storing the alerts from ZTF. They're all giving you some way of filtering them. They're all giving you some sort of transmission capability downstream. And that is a problem because that's essentially work duplication rather than sort of code sharing. So it's not very efficient, but it's also creating an ecosystem where there's a whole bunch of services, each of which have a different API that may or may not be compatible in any way, shape, or form. And it takes a lot of development effort to sort of build something, a pipeline around all of this that can work. So you already saw that with some of the downstream elements. If you're a survey group that is interested in, say, follow-up, so something like Andy Howell's Supernova Exchange project, or Fritz, which you heard about from Dimitri Duev in the ZTF team, or the Young Supernova experiment that I'm a part of, the question then becomes, well, which broker do I go to? What if they don't all have exactly the same capabilities? Do I have to sort of go to some combination of them? If I want to trigger telescopes, then, well, there's a TOM toolkit to do that now, but there's also this Aeon thing that's under development for Gemini. There looks like there's other efforts that will be happening to trigger smaller scale telescopes. And so the question then is, again, what should you support? How do you even communicate all of this data to each other? So here at SCiMMA, people have been building out this hopscotch system, but of course, ZTF is using Kafka. LSST looks like it's currently using Kafka. Hopefully that will change. But there's all this talk about, how do we use machine learning to interpret people who still want to write GCNs as text notifications. And I'd argue that that's, a very, very hard sort of ecosystem to build when it's this fragmented. It's very hard to sort of build a cohesive multi-messenger astrophysics pipeline and analysis system if you have all of this different stuff in there. And so right now, even to do something like identify an interesting source in the alert stream, I had to go to TNS. And then I had to get the RA index. I had to get that RA index to get the archival photometry for the source from Antares. And I can still use Antares to sort of find similar objects. But if I wanted to do sort of archival photometry on other missions, say HST photometry, I would have to go specifically to MAST. And even there, I would only be able to get the images. I wouldn't necessarily have any resources that says, give me force photometry at this location for this interesting source. So there's potentially images out there that might tell me something about what this TDE was doing several years before this explosion that my colleagues at Northwestern noticed. But we won't know because there's no easy way to get that data out of an archive. So this seems to me to give us some use cases for sort of an interlinked ecosystem that's a lot more integrated than it currently is. We are currently doing things like augmenting this alert stream with historical data, but we want to also sort of like discover pre-explosion outbursts or really rare repeat events. We want things like high proper motion sources, which will require an extraordinarily long time baseline. We want joint pixel processing. So for example, LSST observes in UGRIZY, and Euclid gives us complementary information in the NIR. And if you could somehow combine those things together, you could actually, for example, do a better job for things like photosys for the host, but also things like studying the stellar populations that are right near the center where a particular transient event happened. And that's, of course, important and valuable information. If you wanted to study the structure function again on long scales, you'd need multi-mission access. In the MMA side specifically, we have this real-time brokering aspect, we have this pub subsystem, but there's not really an easy way to coordinate and share limited spectroscopy resources. There's this treasure map service that you've heard about here on other SCiMMA talks that shows you what people have made public, but there's no sort of unique coordinating hub which says over something like hopscotch, so-and-so has identified this particular object as a gravitational wave counterpart candidate and has triggered observations with this telescope. That sort of suggests that you shouldn't be observing the same source, and we should, in the very limited time we have to, say, follow up a neutron star merger, a kilonova, as it rises and then fades very quickly, we should try to cover as much of the sky as possible. And there isn't any way to do this right. If you even just wanted sort of like a resource that gives you all photometry from all surveys at some given RA and DEC, there's the NOAO archive that will give you the images. You have to download terabytes of images, come up with some kind of computing resources to load all of those images up, deal with the fact that all of them have different Fitz header keys and whatnot, and actually go get force photometry from all of those sources and build that into a reasonable light curve to study any event. So archives don't actually do this. The closest thing that does that has been proposed to do something like this is something that people are calling a survey science platform, essentially a kind of a Jupyter hub environment where you can run custom jobs on large quantities of data, potentially in the cloud, but potentially on some high performance computing cluster. And these are again proposed for individual surveys, things like LSST by itself. There isn't really a multi-mission version of this. And the closest thing that there is MAST. So I'd argue that as ground-based surveys are getting bigger and bigger, this is the need that we need to address as SCiMMA. This is the infrastructure that we actually need to build that needs to scale. And this is sort of my pitch to building this. So what I think we want to build is an infrastructure called a data lake. So a heterogeneous collection of images and spectroscopy from existing surveys. So in that respect, kind of like an archive, but with other stuff on top of that. So we don't want just to be a dump for everybody's existing data. We want some valuable higher level science products, including things like catalogs and databases on top of that. And we don't want to give people access to just the raw data by itself. You want to be actually providing sort of the facilities that brokers are doing combined with things that we would like but still don't have. We would, for example, love to have this Jupyter Hub environment so that you could deploy a notebook that can run across a huge quantity of images, but do it on the cloud. You might want to have analysis and visualization tools, look at this data and sort of make a quick and dirty plot that you can share with your colleagues. So you also might like something like some kind of identity management for all of this so that you can share some quantities of data only with certain groups, but you might want to make other stuff public. You might also share not just the data, but also actually your workflow. So for example, if you build a force photometry Jupyter notebook, perhaps that's something that you can make public and share with other people on there. And of course, because there's a huge amount of data here, we don't necessarily want to be downloading this all to your work laptop, but that facility needs to exist for the users that demand it. And of course, given that we are talking about MMA, it'd be really helpful if we could also not just allow downloads of data, but also people to submit data into this cloud. So imagine we are in a future where we have not one neutron star event, not one kilonova, but a few. And at this point, it's important to actually build a good model for these events and to say, understand what the equation of states of neutron stars are that's underlying them. At that point, you might like theorists to be able to submit their particular model for an equation of states so that you can, within a single framework, take their model, compare it with all of the existing GW waveforms, and effectively do a chi-square test to see which one is the best supported by the data. That's a sort of a reasonable thing to do and involves not just observers, but theorists. And there is no infrastructure to do this, right? So the Amazon version is that a data lake is a centralized repository that you store structured and unstructured data. But I think in astrophysics will be largely dealing with this unstructured case. And you don't have to sort of go around and build a complex structure and index for all of the data. You really want to sort of give people access to tools, dashboards and visualizations to do big data processing and the sort of real-time analysis and machine learning. And so this is a different sort of structure from something more traditional like MAST or the NOAO data archive. It doesn't necessarily have some kind of optimized SQL to return a whole list of images that match some particular array in deck or are in some box. But it allows you to have some sort of easy programmatic access to the different holdings. That's the key part that ends up being needs to be developed in the data. There's plenty of prior art for this sort of stuff. So SDSS, this is a query that I think I was using all through my graduate studies, but it essentially sort of gave you the ability to sort of select out galaxies and stars and get spectra for particular objects within SDSS footprint for a huge amount of area or for a custom list of objects. So incredibly powerful catalog-based access to all sorts of useful quantities provided through SQL. MAST, rather than doing catalog-based access, is a thing that gives you access to actual imaging data products from multiple missions. So where CAS jobs really only gave you access to SDSS data, MAST doesn't give you anything like the actual photometry. On the previous slide, for example, I had the Divacular's radius for different sources in there as one element in my query. I don't get that with MAST. I get a list of images, and I have to sort of download them and do the analysis on my own. But the powerful thing about MAST is that list of images is not just the space telescopes like Hubble, but it's a whole bunch of different missions. And so there's potentially a huge amount of data on a given source. So this was for the Crab Nebula. We also want some systems that can actually run in response to actual alerts that we're getting live from a telescope. And so we've actually built an example of this called GHOST at NCSA for ZTF. This is built by my graduate student, Alex Gariano. And Alex takes new ZTF events that get reported to the transient name server that I showed you earlier, and simply tries to identify what the host galaxy is automatically. Now, at first blush, you might say, well, that's an easy task. Why don't you just do a cone search and figure out what's nearby? And that will work for more or less most of the distant objects. The problem happens, of course, when you are not in the distant universe, but you're really looking at nearby sources, like this one supernova that's marked by this yellow star. In that case, there's not just one object that's nearby, there's several that have close catalog matches. And so what Alex needs to do is download postage stamps for all of these sources, measure things like their half-life radius, associate the supernova with a particular source in real time, and then go off and try to find spectra and whatnot for that extra source. So this is happening live for a whole bunch of alerts as you get data out of ZTF. And that's, again, something that we built as a custom service for this one project. There's no easy way to do this more generally. But you can imagine that there are plenty of other things that you might want to do generally using things like postage stamps or the light curve coming in from brokers. And there's only sort of the limited compute that brokers currently give you, which operate only on the alerts themselves. If you want a light curve, you'd better be aggregating all of those alerts at a particular location together to actually even build that light curve. If you want things like access to postage stamps and AstroPy to say do image manipulation, then currently you are bluntly out of luck, unless you build something custom. DES has a nice mixture of public and private data access, but again, specifically for DES. So much like MAST and CAS jobs, it gives you access to DES data products, but it also lets you have a Jupyter Hub sort of like environment. And so you can sort of see that people are already building layer upon layer of these things together to get closer to what a data lake looks like. And so there are options to sort of run a Jupyter Hub environment right at NCSA or at the NOAO Data Lab that give you programmatic access to things like cutouts or data in services. And this is starting to look a lot like what we have with this data lake. Like you have a front end which you can look at through your web browser. People can submit jobs to a job handler in the back end, either through the browser or through something like a Jupyter Notebook that spins up Kubernetes instances. One user might want something like a cutout of a particular region of the sky. Another might be doing something like a cast jobs query. You might also want to have something like this Jupyter Lab environment where people can launch their own jobs. But again, this is all for just DES data. There is no multi-mission support here. And so there is still space for this concept to sort of become a little bit more flexible than it is. Plus, all of the data that it has is all sitting on a disk. It's not dealing with a real-time alert stream like you will get with ZTF or LSST. There's no continuous updating of what you're looking at. Nevertheless, these things are getting to the point where they really are giving astronomers sort of tools they just did not have even 5 years ago. So Kubernetes in particular lets you sort of look at a whole bunch of these services through a simple browser and simple front ends that people can customize and submit off jobs that go and do pretty powerful things on the back end without the user essentially having to develop all of this infrastructure for just their project, which is kind of how we have been operating thus far. And so I can actually even give you a quick sort of demo of the DES access site. So let me do that. So I should mention, especially as a former NOAO employee, that you can also do this sort of stuff through NOAO's data lab. So if you log in there through Astro Data Lab, you can launch a Jupyter Notebook in much the same way. I'll have a bunch that will show up in my own user account space. And this is all tightly integrated with services like Antares. So for example, if you want to develop a filter for Antares, say you're working with a group like Ogle, like I was a few months ago working on a microlensing filter, you can launch a Jupyter Notebook that essentially beta tests their entire filter for them. So you can load up an Antares dev kit, you can set a Slack ID, you can look at Lucas's particular criteria for a microlensing event. So in his case, he's doing a parametric fit to individual light curves and deciding if they match certain criteria or not. And all of this is done live on real alerts from ZTF. You can test it in this nice data lab environment, but we still have this problem where there is a separation in the sense of you can do all of this running live on Antares, but to actually test it, you have to go to a separate service in the sense of data lab, which has its own access credentials, and the two aren't really well integrated at all. There's no way to say submit a filter from this Jupyter Notebook directly into Antares right now. There's no way to sort of export a whole bunch of loci alerts from Antares into Data Lab and say, build a filter around that. There's no connection with the NOAO archives, so you can't necessarily take ZTF alerts from one place and cross them with existing images that are taken with, say, DECCA. So DES in that respect is a little bit more integrated because in the DES case, everything is at least all working with DES data. And so you can run things like your cutout service. If you want to do for any particular region, you can upload a CSV file or find particular events, find particular tiles in there. There's schema descriptions of all of the different tables that are in DES. So much like in SDSS, you can do large queries across DES to sort of get a whole bunch of useful properties that people have pre-measured for you. But again, there's no connection here with an alert broker. There's no live processing of alerts, and it's purely DES data. There is no multi-mission data access. Um, so essentially building this data lake would look like building an image server that has multi-mission access, is maybe connected with something like Amazon Web Services, so you can do things like submit jobs to train your deep learning models, or do massive catalog cross queries, all in the cloud or in some HPC resource, say clusters that you have access to at NCSA. And that lets people do things like model evaluation. So again, if you wanted to see which equation of state for nuclear matter actually describes gravitational wave events, then this is sort of the say infrastructure that would actually enable tasks like that. And we don't have a nice way of doing that yet, but that's sort of where my pitch is going, is how do we actually build this? And this is, again, just a quick example of the same data lab thing that I showed you, except here for me developing my filter to actually find gravitational wave EM counterparts. This is something that a postdoc in our group, Deep Chatterjee, has been working on more recently. And so hopefully in the next month or so, you'll see Antares have an updated gravitational wave filter that has a new model for gravitational wave for kilonova for the light curves, and is hopefully better at identifying these events even earlier as they go off when you get a LIGO alert. And so that should be relatively exciting, and hopefully something that brokers can do. But again, we're only operating on ZTF data. We're not really using any archival data, despite the fact that NOAO has several terabytes of archives from existing servers. So my takeaway then is that there's no single science platform that combines archive access, a broker system, sort of marshal system for an individual group to sort of decide if a particular object is interesting, like you heard from Dimitri last week. And that's a resource that this community desperately needs. Without it, what is happening to survey data is that it's going into sort of a data swamp or a data orphanage, if you like, and it's become stale and it doesn't really get use. It's sort of like having a whole bunch of FITS images on, a tar tape. It's nice in principle. You can always be reassured that you have that backup, but it's sitting there and doing nothing. Hopscotch, which SCiMMA has been spending a lot of its effort developing, fixes how these sort of different services can talk with each other. But it doesn't actually tell them what to talk about. It doesn't really start a conversation to sort of integrate these services together. And I think there's enough prior art here that we can define sort of what the use cases are in sort of a big picture vision, but also a more detailed technical description of how to sort of integrate these things and actually build a data lake. Now, this is going to be a hard challenge. And so I suggest doing this not very broadly, but rather specifically in the MMA domain. And I think at this point, it sort of makes sense to actually like request funding to sort of build out this thing in an SSF proposal, because it's literally scalable cyber infrastructure for MMA. And so I'll stop ranting there.
Thanks very much, Gautham. That was very provocative is not the right word. Thought-provoking.
Yep.
I see we have hands up already. Andy, you have a question?
Yes, thanks, Gautham. Nice talk. And Amy, you're thinking along the same lines. Many of us are thinking. You're right that all of these things do need to be built. And some of those we are really thinking hard about, in that, like some of the things like, say, explaining that you're going to observe some particular target. That's the kind of thing that there's no real place for right now. Or even, let's say that some facility is available, like there's a certain instrument on. These are kinds of things that we, I at least imagine going through Hopscotch at some point, but we just need to define a sort of standard and format for that we will get to. It's just too early to do that at this point in development. But and then some of the other things, you mentioned, toms, and they can do some of those things like requesting observations, and then even gathering together archival data. I imagine much of that being done in the tom, like, there's a new transient discovered, the context, some of that comes from the brokers, some of it comes from going in and checking archives. but the TOM would be the place to display a lot of that. And then regarding the sort of data lake kind of thing, we did have this exact idea in, I can't remember if it was in our original proposal for SCiMMA, or if we certainly had it and discussed it. At some point we downscoped because there just wasn't enough money. Like NSF said, okay, you can't do all of this. Here's the amount of money, focus on one thing, and we had to descope. And so that is exactly the kind of thing we want to do in the long term. Right now, we just are forced by the NSF to focus on one particular thing. So I encourage you to think along those same lines, instead of just here's everything we don't have. What is the thing we need for multi-messenger that is sort of not in the current game plan that we need to add on and focus on as the very next step?
So I guess the part that I didn't communicate as clearly as I could have is that people are already, including you, have already built many of the pieces here, in the sense of we have a bunch of the Lego bricks to assemble the full set. And this next NSF proposal that goes in, I think, shouldn't be developing the system from scratch, but it should really be looking at integrating what's already out there much more tightly. And we have the use cases, like you said, from the previous proposals, plus people who talked about this. There's been, Kavli meetings on this sort of stuff. But I guess what I'm trying to do is build a sort of momentum to actually push this from a vague conceptual idea to let's have a dev team start looking at what existing options are out there. And before VRO in particular turns on, have something that's scoped specifically for MMA to do this.
Yes, I agree that now is the time to start talking in more detail about all of these things before there's any future proposal. So yeah, thanks.
Well, I think, thanks, Andy. I think Mario's next.
Yeah, thanks, Gautham. This was it's a very nice summary of kind of what I also believe where we need to be going ultimately. And there has been a lot of work over the last 2 years on this concept. I think you were at the Petabytes conference, the last in the series in Boston, and one of the things that grew out of that was that Arfon Smith was invited to give a talk before the Decadal Survey Committee, where he illustrated or kind of proposed this concept to them, and we started calling it the Astronomy Data Commons rather than Data Lake, just because NIH actually had a similar initiative about 2 or 3 years ago, maybe it was a bit more than that, for NIH Data Commons, where the idea is to put all the data in the cloud. Once you effectively collocate the data in the same data lake, it becomes much easier to build services around it. So to go to your last bullet point, one of the things that we're pushing with that presentation with the Decadal Survey Committee is to argue for a need for a pilot study on the NSF side that's similar to the NIH study to try to understand how far we can get with it. And we're all eagerly waiting to see what kind of recommendations are going to come out. Now, sorry, I'll just one thing and I'll stop my monologue. Now, one thing that didn't stop us from doing is actually trying some of these things out. There have been smaller proposals that have gone into the NSF that to fund the bits and pieces of this. So one of the things we've done is we have ZTF on AWS, all of the data, and the folks at IPAC are now working on, I think they'll show on ADAS that they've ingested in similar architecture, NeoWise. And so one of the kind of crowning achievements of this, if it works out by the end of the year, will be we're going to run a query that will, in an online fashion, do a join between NeoWise and ZTF, where NeoWise is owned by one institution, ZTF by another, and everything happens in the cloud. So I think there's a lot of momentum behind this, and we should find some forum or some way to get all these different groups together so that we start coordinating.
Right, and we've been doing something very similar here. So rather than AWS, I spun up a Vultr instance with a postdoc of mine, Konstantin Melanchev, and we've been cross-matching ZTF DR3 with existing catalogs of variable stars. So VSX, from AVSO, but also anything that was in SDSS. And there's a real reason to do this for VRO. Some of you folks might have heard about the LSST plastic challenge last year, where we simulated something like several million transient events, but also variable events to see how well the public could classify these things. And the challenge was very successful. The results paper is out there. But one thing we found is that we didn't have a lot of the actual classes of variable stars that existing surveys find and can occasionally get mistaken as faint transients, particularly if they're sort of not periodic variable stars, but things that have flares or outbursts. And so doing the sort of cross match, again, sort of needed us to build some custom infrastructure to get it done, but was really so that we could identify decent models for flare outbursts within ZTF, which doesn't have classifications, using existing surveys that do have classifications. And having a general facility to sort of build these sort of tools, these sort of models regularly is I think something that should go into the, like, you know, scientific justification for something like the service in the near future. I think there is a case for waiting for listening to NSF and what their feedback is, whether we should go ahead. But, you know, also at that Petabyte Science to Science meeting in Boston, I think there were folks that had started working on a paper. I believe you were leading it at one point, Mario, that sort of described this stuff. And I don't know whatever happened with that effort, but it sort of stalled. And I think maybe fleshing this out in that paper sort of form is the next best thing to do.
That turned into the presentation for the cable survey, because unfortunately there was no time to turn it into paper. But yeah, I agree with you. We're not waiting for on anyone. This is getting done, and that's why I kind of think we should create some kind of a forum to make sure that different efforts that are going on in parallel are somewhat coordinated. I'm actually against setting standards at this point, because I think it's too early, and it leads, you know, and down certain paths we've tried before and didn't quite work out. But I think we should try out a number of things in coordinated fashion, see what works, and then that will become a de facto standard.
Right. And I think much like Hopscotch is going, SCiMMA should really take the lead here, right? So this forum can be as simple as a Slack channel within the SCiMMA Slack, and having a few people work on this sort of stuff in the hack sessions to sort of maybe not build a prototype even, but build something that at least presents the big picture to anybody else looking at it, is a good thing for us to do over the next few months.
Yeah, I have some thoughts about this as well, but I would save those for if there's time at the end. So next is Dan, and then after Dan, it will be Rachel.
Yeah, so I was just going to say that the singles, well, sorry, in terms of the first bullet that's on the slide, the NASA archives are working with a consultant to try to figure out how they could build a single stop science platform across their archives, which is not everything that you're asking for, and it's not even everything in terms of archives, it's just the NASA archives. But it is, I think it's some progress, and it would be interesting to, I think, watch what comes out of there and try to figure out how can NSF and other data be added on to that, so that we do get to something that's more uniform.
Right, and I agree with people doing this on archives, but the thing that MMA needs is a service that's also integrated with real-time alert streams, and that's a much bigger challenge than archival data that's sitting on a disk, because you don't have a database that's continuously growing every single night, right? And so that the extra complexity from dealing with real-time alert streams is not negligible, but it's sort of the critical thing for MMA.
So I guess the reason I was saying that was maybe to follow up on somebody's earlier comment about not necessarily trying to do everything at once, but trying to do different pieces. And so if there is a piece that's coming out in terms of science platform and multiple archives, maybe the piece that's needed then is, all right, a science platform and broker, so that those then can get merged together after we build up in each one.
Yep.
Okay, thanks, Dan. I think Rachel has a question or a comment.
Hi, so I wanted to reiterate the need for interoperability between these, which obviously is a number of people said, but I wanted to emphasize the need to reach out beyond just a few communities. And I don't know if having a subset of the SCiMMA forum will actually do that, because a lot of different communities are actually pushing in these directions. And interoperability would allow us to actually make that work for lots of different science cases and allow the whole system to grow organically. But I wanted to point out especially the LSST in kinds process is encouraging the international community to build data access centers, particularly for LSST data. And on the LSST rules, this is supporting the science platform, but not the LSST Lite DAX, as opposed to the LSST full DAX. And what they will serve and how they will serve it is very much up in the air at the moment. And many of those brokers are coming from very different communities, well outside SCiMMA. And many of them are completely unfamiliar with this community. So we run the risk of proliferation if we're not careful here.
So I agree with you, and actually I guess part of the motivation for this talk is the LSST in-kind contribution deadline was relatively recent. And with my LSST desk Supernova working group lead hat on, I was looking at a whole bunch of these in-kind contribution proposals for telescope time in particular from different groups. So, you know, projects like TIDES and POMOS, things like PFS. And I sort of recognized that coordinating those different groups was going to be an absolute nightmare that DESC has not really factored in thus far. And so we put in some language about, you know, coordinating observations between different groups such that we don't get 20 spectra of the same supernova. But doing it even for DESC is a hard challenge because the scope is so large, like you said. There are many different parties. That's both the strength and the weakness of doing it there. You'll have to listen to a lot of different voices in this. Whereas building something more purpose-built, more bespoke for just multi-messenger astrophysics, that's a more bite-sized project that won't go too crazy in scope, but is hopefully an example for groups like DESC to build into an even larger system. So I'm not suggesting that we try to tackle the full problem head on right out the gate. I'm suggesting specifically focus on the MMA aspect and doing this for multi-messenger astrophysics because that's tractable.
I understand where you're coming from, and speaking with my transients and variable stars science collaboration hat on at this point, I completely support that. It's a great idea, but I would like to encourage us to make these tools as generally available as possible and as adaptable as possible. And I think the easiest way to do that is to make it in such a way that you can take a section or a tool that might be useful for your particular branch of science and apply it in your way and make those tools interoperable where we need to, because that's the way you can grow most organically without trying to have a one ring to rule them all type solution.
Well, I think we're in violent agreement, actually.
It sounds like it, it does.
Yeah, I think actually, so Patrick has his hand up as well, and obviously he's been leading the strategy side in particular, so he might have some comments on that too.
Well, actually, it was more just I was going to ask Rachel, you know, we're all so busy and we can't get together. A workshop is always a good way to try and kick off people's collaborations, but we're not going to be able to do that in a real way. So you know, I think one of the things that'd be nice would be to identify 1, 2, 3 other groups that are not connected yet, but perhaps are good high priorities and align somewhat with MMA, and let's have a conversation. So if you can help to make that link, I think it would be fantastic.
Absolutely, I'd be happy to.
Patrick, can I also quickly interject here and point out that Francisco Foster, who is the lead for the Alersi broker, has been in touch. He and Anais Moller, who work on the Think broker from France, are actually organizing a broker workshop later this month. It's the October 27th and 28th, if I recall correctly. And they asked folks from SCiMMA to please present about hopscotch. But most of that that workshop is in fact focused on discussions. And so that might be a good venue for you to jump in and actually talk to some of these teams that are more broadly focused on time domain, astrophysics, and how we can evolve from brokers to this more rich ecosystem.
Yeah, great. I mean, I think that's great. And I do think, Gautham, just to go back to your presentation, I do think that picking off sort of the next place, hopscotch is progressing very nicely, and sort of there's a plan there and it's moving. We need to take it up a notch, I think, but it's got some real solid work done. But it'd be nice to identify what's next for us. And I think the other thing to do is that I really, there's one thing that always motivates researchers, and that's if they think there's some funding available. So to some extent, if we can figure out, which group could do with some help, whether it be in, really getting some of the skills that are available through this group now to help out, or in bootstrapping them to be able to use different tools to do development or whatever, I think maybe we can find a path that way as well. I think we just need to find the next best place to put our foot. Hopscotch was easy. It was a real gap, I think, but the question is which of the gaps can we help fill now? There may be smaller.
And I completely am developing a very fine understanding of this funding situation as junior faculty now, and there are folks at NCSA that I would love to work with and start to build this stuff out. But I have some time and summer salary. They need to find that time and summer salary to actually do work on this project. And that's why I ended this slide with that last bullet. I don't think we can sort of pretend that funding isn't important, and we have the ability to start building this out at this point. But it's a question of finding the funding for the right people to actually focus on it in the short term.
Yeah, and I think it's a bit like evolution, isn't it? You want to end up with an eyeball, but how you get there in a whole bunch of stages, each of which offers advantage over the previous one, that takes some planning.
I just wish all of you folks had told me this while I was still a postdoc, so I didn't have to do this. Nobody warned me. So
I think we're closing in on the hour. So we have Andy and then Mario have their hands up, and if between you could be done in sort of 4 or 5 minutes, that would leave us able to wrap it up.
Yeah. So I wanted to say we're struggling with one thing in hopscotch, and that is we don't want to carry all of the, let's say, LSST alerts because their brokers are doing that. We want to get stuff downstream from the brokers, but I don't think there's really a standard for what we get out. Like if we wanted to say, okay, just give me all the type 1As or things you think are type 1As, or give me all the, I don't know, things in this localization region or something like that. Right now, the world is relatively easy. You go to GCNs or you go to the ATELs. I mean, do you imagine some standardization of what's coming out of brokers, or is there a, how do you imagine that working?
There already is effectively standardization because ZTF use Kafka. And so all of the brokers right now are using the same sort of format for what their output is. That's relatively straightforward to convert from Kafka to hopscotch. It's also relatively straightforward to extend the alert packet that comes from a source like ZTF or LSST by simply adding on records to the same alerts package. And you can do more fine-grained divisions like create topics specifically for type 1A supernovae or whatever. So I am actually quite happy right now with the format of things. I think the ZTF team made a really, really prescient choice. And Maria Patterson in particular, who did a lot of that work to get this stuff up and running. It was a fantastic choice that she made, and kind of why I think this ecosystem has worked as well as it has. But it's now getting beyond just the formats and actually getting these different systems to really talk together. That's the hard challenge. That's the next challenge.
Okay, and Mario will have the final question.
Well, I just wanted to say that although we technically have descoped a lot of the research platform for parts of the proposal, we will deploy something in the next year. And just like with Treasure Map, we didn't wait for funding to try to get that developed. There is a lot that has been done that I think we can apply within SCiMMA and then show how to integrate it. This integrated system works, where we have both the alerts and the databases all sit in the cloud with actually a user interface that allow you to access it and do rich analyses. So I'm looking forward to that in the next, I'd say 6 to 9 months we'll have that.
Can I quickly get a clarification from you, Mario? When you say things were descoped, that was in the original SCiMMA proposal, right? Not whatever the next one is that's going to go in.
Yeah, that was in the one that we're on right now. Yeah.
Yeah. Okay. So when is the next proposal deadline? When is the next SCiMMA NSF proposal?
That's an excellent question.
Yeah,
That's kind of my motivation.
I think we live in absolute fear that somebody's just going to pop out a solicitation tomorrow and it will be due next week. So the truth is, we've been told by NSF that it's imminent that some form of solicitation, imminent. Sorry.
Yeah.
They are trying to match the schedule they've been planning, which was a very aggressive timeline, with a notion of having solicitations come out now for, say, spring. Or this winter. And so, as I say, I think we seriously are living in fear of seeing the solicitation.
But it's, I mean, it sort of made sense, I think, to descope it in the original proposal. It was pretty clear from the meeting at the University of Maryland that resulted in the Allen et al. Paper that, we didn't quite have all of the bits that we needed to build a really grand system at that point. But I think now we can build something that maybe doesn't do everything, but again connects up what we already have much more tightly. And so this feels like the times to strike.
Yeah. So Patrick, your hand's still up. Did you have any final things you wanted to say? Oh. Okay, so falls to me then to thank you again, Gautham, for this really thought-provoking talk and discussion.